Something is amiss in our comprehension of the universe. Cosmology is, by all accounts, heading for a confrontation on one of its most essential inquiries. How quick is the universe expanding? For more than a decade, two kinds of estimations have been in conflict. Perceptions of the current universe regularly find the rate of expansion, called the Hubble constant, to be around 9% quicker than forecasts based on early universe data. Specialists trusted that the James Webb Space Telescope, the most advanced telescope ever built, would help settle the inquiry once and for all. However, consensus has so far failed to appear. Rather, the Space Observatory has solidified the inconsistency with incredibly exact groundbreaking perceptions that threaten to affix the standard model of cosmology. The new physics expected to alter or even replace the 40-year-old hypothesis is now a subject of debate. An astonishing and intriguing possibility is that there's something we do not yet comprehend about the universe. Join us as we dive deep into how new ultra-deep pictures from James Webb have just confirmed that there is something truly amiss with our understanding of the universe. Our universe began with a bang, the Big Bang. Energy, mass, and space streaked into reality all within a momentary moment. Then, the youthful universe was formed. A growing, roaring plasma stock of matter and antimatter particles that jumped into reality just to obliterate each other upon contact. Left to their own devices, the matter and antimatter inside this plasma should have consumed each other altogether. Yet, researchers believe that some unexplored world irregularity empowered more matter than antimatter to be produced, saving the universe from prompt implosion. Gravity compacted the plasma pockets, pressing and warming the matter so that sound waves traveling just over around 50% of the speed of light, called baryon acoustic oscillations, undulated across their surface. In the meantime, the high energy density of the early universe's packed contents expanded spacetime. A little part of this matter safely survived the fry as the universe expanded like an inflatable. The standard story goes that ordinary matter, which interacts with light, solidified around clusters of invisible dark matter to make the first worlds, connected together by a tremendous infinite web. Initially, as the universe's substance spread out, its energy density, and consequently its extension rate, diminished. However, about 5 billion years ago, galaxies began to subside once more at a consistently quicker rate. The reason was another undetectable and strange substance known as dark energy. The simplest and most well-known explanation for dark energy is that it is a cosmological constant, an inflationary energy that is the same everywhere and at every moment, woven into the extending fabric of spacetime. Einstein named it lambda in his theory of general relativity. As our universe developed, its general matter density dropped while the dark energy density remained the same, progressively making the latter the greatest supporter of its overall extension. Added together, the energy densities of ordinary matter, dark energy, and energy from light set the upper speed limit of the universe's extension. They are also key ingredients in the lambda-cold dark matter, lambda CDM model of cosmology, which maps the evolution of the universe and predicts its end, with matter eventually spreading so far that it encounters a thermal death called the Big Freeze. Many of the model's predictions have been demonstrated to be highly accurate. However, here's where the issues start. Regardless of much looking, space experts do not know what dark matter or dark energy are. As Afra Love, a professor of astronomy at University College London, who is engaged in world studies of dark energy, said, "A great many people agree that the universe's present composition is 5% ordinary nuclear matter, 25% cold dark matter, and 70% dark energy. The humiliating truth is we don't comprehend the last two of them yet. An even greater threat to the lambda CDM model has appeared. Depending on what technique astrophysicists use, the universe seems to be expanding at different rates, a discrepancy known as the Hubble tension. Techniques that peer into the early universe show it expanding significantly quicker than lambda CDM predicts. Those methods have been checked and confirmed by innumerable perceptions. As a result, Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the new James Webb estimation, said, "The only reason I can understand for them to differ is that maybe the model we have between them is missing something. Estimating the universe's extension takes a bit more than a radar gun." The principal method to measure this development looks at the so-called cosmic microwave background, CMB. a remnant of the universe's first light produced just 380,000 years after the Big Bang. The imprint should be visible across the whole sky, and it was planned to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this astronomical baby picture, the universe is mostly uniform, but hotter and colder patches, where matter is more or less dense, reveal where baryon acoustic oscillations made it cluster as the universe detonated outward. This soap bubble structure swelled into the cosmic web, an organization of jumbling strands along whose convergences galaxies would be formed. By concentrating on these waves, cosmologists deduced the amounts of ordinary matter and dark matter and a value for the cosmological constant or dark energy, resulting in a standard model that disagreed with a Hubble constant of about 67 kilometers per second per megaparsec. We should stop on this number for a moment. If a galaxy is a distance of 1 megaparsec away from us, it means it will retreat from us and we from it at 67 kilometers per second. At 20 megaparsecs, this downturn grows to 1,340 kilometers per second and continues to increase dramatically from that point forward. If a galaxy is any farther than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A second technique to find this development rate utilizes pulsating stars called Cepheid variables, dying stars with helium gas outer layers that expand and contract as they absorb and release the star's radiation, making them intermittently glow like distant signal lights. In 1912, cosmologist Henrietta Swan-Leavitt found that the brighter a Cepheid is, the slower it will pulse, empowering cosmologists to gauge a star's absolute brightness and hence check its distance. It was a milestone discovery that turned Cepheids into abundant standard candles to measure the universe's massive scale. By hanging observations of pulsating Cepheids together, space experts can build infinite distance ladders, with each rung taking them a step further back into the past. It's one of the most reliable methods that space experts have today for measuring distances. To construct a distance ladder, astronomers build the first rung by picking nearby Cepheids and cross-checking their distance based on pulsating light. Wendy Friedman, an astrophysicist at the University of Chicago, stated that the following rungs are added utilizing Cepheid readings alone. Then space experts look at the distances of the stars and supernovae on each crosspiece and analyze how much their light has been redshifted, stretched to longer, redder frequencies as the universe extends. This gives an exact estimation of the Hubble constant. In 2019, the technique was used by Rees and his teammates, who trained the Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was an unthinkably high development pace of 74 kilometers per second per megaparsec when contrasted with the Planck estimation. However, Hubble missed the mark on fundamental accuracy for the crowded regions of space the group was studying, causing some distant Cepheids to obscure into adjoining stars. Disagreeing cosmologists had some room left to argue that the result, while stunning, might have come from a measurement error. So when James Webb launched in December 2021, it was poised to either determine the error or cement it. At 6.5 m wide, its mirror is just over 3 times the size of Hubble's, which is only 2.4 m wide. Not only can James Webb detect objects multiple times fainter than Hubble can, but it is also undeniably more sensitive in the infrared range, enabling it to find a wider scope of frequencies. By contrasting Cepheids measured by James Webb in the galaxy NGC 4258 with bright type Ia supernovae, another standard candle, since they all explode at the same absolute brightness in distant galaxies, Rees and his partners arrived at an almost identical outcome, 73 kilometers per second per megaparsec. Different estimations, including one made by Friedman with the Hubble Space Telescope on the rapid light of the most luminous tip of the branch red giant stars and another with light bent by the gravity of massive galaxies, returned with particular outcomes of 69.6 and 66.6 kilometers per second per megaparsec. A different result utilizing the bending of light also yielded a value of 73 kilometers per second per megaparsec. Cosmologists were left reeling, as indicated by Ronil K., a cosmologist at the University of California, Merced, who has been working to explain the Hubble tension. The CMB temperature is measured at the level of 1% accuracy, and the Cepheid distance ladder estimation is approaching 1%, so a contrast of 7 kilometers per second, while not especially large, is incredibly unlikely to be a random opportunity. There is a significant implication. To explain the new outcome leaves the response wide open, splitting cosmology into groups pursuing vastly different solutions. Following the Hubble Space Telescope result, an official attempt to resolve the issue at a 2019 meeting at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As the late Vera Rubin, who found evidence for dark matter, said at the time, "No one wanted to give up their toy. Each person involved believed so strongly in their own results and so firmly in the way that their observations and their measurements were done accurately, it just left people wanting to figure out how to explain this." In February 2023, with James Webb and another independent Hubble Distance Ladder result affirming the Hubble tension, cosmologists were left with three potential explanations: measurement errors, new physics, or some combination of the two. Kay explained that most of the data supports new physics. The simplest and most well-known speculation is that dark energy behaves differently today than it did in the early universe. If dark energy was strong at one time and then faded, it would make the universe look smaller when we look back to the early universe, making the extension rate appear quicker today. There are different explanations, such as the possibility that there are two kinds of dark energy or that dark matter interacts with light. However, these explanations present complexities that cosmologists are cautious about without further information. Dark energy and dark matter aren't the only mysteries James Webb is helping to solve. When it launched, it was tasked with looking further back in time than any telescope before it. James Webb's revolutionary new imaging technology empowered it to see galaxies formed just 300 million years after the Big Bang. However, while examining the universe's beginnings, space experts found that these early-stage galaxies are undeniably more massive and developed than the standard model predicts. Early galaxies should have been filled with youthful, hot stars forming at a very fast pace. Yet James Webb showed that many of them were overflowing with heavy elements from prior ages of stars and actively developing swollen centers of very massive black holes. James Webb's observations have intensified the debate in cosmology by providing precise data that affirms existing inconsistencies and reveals unexpected insights about early galaxies. Resolving the Hubble tension and understanding these early galaxies could require new physics or a significant modification of the standard cosmological model. The pursuit of these answers is perhaps one of the most exciting frontiers in modern astronomy. The James Webb Space Telescope, JWST, has not only revolutionized our understanding of early galaxies, but has also opened new avenues for exploring crucial questions in cosmology. Its infrared abilities allow it to peer deeper into the universe than ever before, capturing light from some of the earliest galaxies formed only 300 million years after the Big Bang. These observations have challenged the conventional thinking about galaxy development, suggesting that early galaxies were not merely simplistic young structures but were surprisingly complex, containing heavy elements and hosting supermassive black holes at their centers. This inconsistency between theory and observation raises significant questions about the processes driving galaxy evolution in the early universe. It hints at processes that were perhaps more rapid and efficient than previously thought, leading to the formation of galaxies with unexpectedly intricate structures so soon after the Big Bang. Additionally, JWST discoveries have exacerbated the long-standing puzzle surrounding dark matter and dark energy. These elusive components, which make up the majority of the universe's content, remain poorly understood. Dark matter, which interacts gravitationally but not electromagnetically, plays a crucial role in shaping the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. Despite extensive efforts, its exact nature and composition remain elusive, prompting ongoing searches through direct and indirect detection methods. On the other hand, dark energy, responsible for the accelerated expansion of the universe, presents an even more confounding challenge. The standard cosmological model positions dark energy as a cosmological constant, uniform in its properties throughout spacetime. However, discrepancies like the Hubble tension suggest that dark energy's behavior may not be so consistent. Alternative theories propose dynamic forms of dark energy that evolve over cosmic time, potentially influencing the universe's expansion rate differently at various epochs. Addressing these mysteries requires not only advanced observational capabilities like those of JWST, but also theoretical frameworks that can accommodate new data without discarding the achievements of the current model. Astrophysicists and cosmologists are exploring various theories, from modified gravity theories to exotic particles and interactions beyond the standard model of particle physics. The implications of JWST revelations extend beyond cosmology into broader astrophysical inquiries, including the origins of life-supporting planets and the conditions necessary for complex chemistry to emerge in the universe.